In this lesson, we will now have an in-depth look at the TLS 1.3 handshake. Again, as a short recap, the overall objective of the TLS 1.3 handshake is the construction of a secure channel from an insecure channel by authenticating the client and server involved in the connection and by having the client and the server agree on a master secret. This is the very same objective as also the TLS 1.2 handshake has, but as we will see, the TLS 1.3 handshake looks significantly different from the TLS 1.2 handshake for various reasons that will become clear later on. The drawing on the left side indicates the various conceptual stages that the TLS 1.3 handshake will go through, and the coloring is again aligned with the coloring used in previous lessons and which should be an aid to map the stages of the TLS 1.3 handshake to the intended cryptographic purpose. The conceptual stages of the TLS 1.3 handshake are the same as within the TLS 1.2 handshake, although the stages are split and ordered differently, which was mostly done to improve the performance of the handshake. Again, this is a topic that we will have a look at in a following lesson. Like the TLS 1.2 handshake, also the TLS 1.3 handshake passes through stages that serve the agreement on a TLS version and on a cipher suite between the peers involved in the connection, and also passes through a stage that serves the authentication of the server and the optional authentication of the client. The TLS 1.3 handshake then also passes through a stage serving the agreement on a master secret. As a crucial difference to TLS 1.2, TLS 1.3 only knows about the ephemeral Diffie-Hellman key exchanges THE and ECTHE, or the use of a pre-shared key. No longer available are RSA-based key exchanges, as it was prominently supported by TLS 1.2. The TLS 1.3 handshake now starts with a client start phase, where the client sends a client hello message and then immediately also sends an ephemeral Diffie-Hellman half key and or a pre-shared key. Very similar to the client hello message of TLS 1.2, the client hello message of TLS 1.3 contains the TLS version that the client desires to use for the connection. Additionally to the desired TLS version, the client hello message also contains a list of cipher suites supported by the client, and where the list is sorted according to the preference of the client. And the last part of the client hello message is a freshly generated 32-byte random number that will be important for later derivation of cryptographic key material. If the client wants to offer the use of a pre-shared key, then the client would follow up by simply also sending a label of a pre-shared key to the server. If the client wants to conduct an ephemeral Diffie-Hellman key exchange, then the client would follow up by sending a corresponding ephemeral Diffie-Hellman half key. At this point, the client doesn't know anything yet about the preferences of the server, so the ephemeral Diffie-Hellman half key sent by the client is just a guess of the client on the preferences of the server. For this, the client has to guess whether the server wants to use the ephemeral elliptic curve Diffie-Hellman key exchange ECTHE or the classic finite field-based ephemeral Diffie-Hellman key exchange DHE. For an elliptic curve-based key exchange ECTHE, the client then needs to guess the elliptic curve, and for a finite field-based key exchange DHE, the client then needs to guess the finite field group. This sounds like a lot of guesswork. Good thing is that the client can actually send multiple guesses within the same message, and given it's nevertheless a somewhat small set of choices to make, chances are that in case the client sends multiple half keys for different combinations of key exchange types, curves, and finite fields, the client will send a half key to the server that the server can support. Once the server received the client hello message and the half keys from the client, the server will check if it can support any of the half keys sent. If the server can't support any of the half keys sent by the client, the server will respond with a hello retry message to the client that contains a half key of its own, with the client then resending a half key of the appropriate type to the server. In case the half keys received from the client can be supported by the server will respond with a server hello message that contains the chosen TLS version, the chosen cipher suite, and as well a freshly generated 32-byte random number that again will play an important role in the derivation of cryptographic key material later on. Following the server hello message, the server then replies with an ephemeral Diffie-Hellman half key of its own, possibly together with or instead of the label of the chosen pre-shared key, in case the client asked to use a pre-shared key that the server could support. Once the half keys or the chosen pre-shared key label was sent from the server to the client and the server then used the HMAC-based key derivation function HKDF to derive a handshake secret and then use this handshake secret to derive with HKDF keys that they will use to encrypt the subsequent messages exchanged within the handshake. Last, the client and the server use HKDF to locally derive the master secret from the handshake secret, with the master secret then forming the base for the later derivation of cryptographic keys used to secure the exchange of application data. Following the agreement on the master secret is the stage responsible to authenticate the server. As just mentioned before, and as you can see on the drawing, each message is now surrounded by curly brackets, indicating that as of this stage, all handshake messages are encrypted with keys derived from the handshake secret. Now, if the TLS connection makes use of pre-shared keys, then the server will actually be authenticated by means of knowledge of this pre-shared key and the finish messages that will be authenticated with keys derived, among others, from the pre-shared key. In all other cases, when no pre-shared key is used, the server is authenticated by sending its X509 certificate chain to the client. In that case, the server immediately sends a certificate verify message, which contains a digital signature across the entire handshake up to this point, and which was created by the server using its private digital signature creation key corresponding to the public digital signature verification key contained in the server X509 certificate. If the server wants to have the client authenticate as well for a mutually authenticated TLS session, then the server also sends a client certificate request message to the client. Receiving all these messages from the server, the client then needs to verify the received X509 certificate chain according to the X509 certificate chain validation semantics as defined in RFC 5280, and additionally needs to then verify the digital signature on the certificate verify message received from the server. In case any of the validation fails, the client must alert and the handshake will terminate. If all of the validations succeed, then the server is successfully authenticated and the client will, if requested by the server, proceed to sending its own X509 certificate chain to the server, together with a certificate verify message containing a digital signature across the handshake that will prove knowledge of the private digital signature creation key to the server. If the server then successfully validates the received X509 certificate chain and the digital signature on the certificate verify message, the client was successfully authenticated as well, then leading to what is commonly referred to as a mutually authenticated TLS session. The conceptually last and highly crucial stages of the handshake are the finish messages exchanged between the client and the server. These finish messages contain HMAC tags calculated across transcripts of the entire handshake. The keys used for this HMAC calculation are derived with HKDF from the ephemeral Diffie-Hellman half keys and the pre-shared keys, and the hash function used within HMAC is the hash function indicated in the agreed-on cipher suite. If the received finished messages then contain the expected HMAC tags, the client and the server then have mutual agreement on the entire handshake exchanged. This assures that both the client and the server arrived at the same master secret, which is crucial as the later application data is secured with cryptographic keys derived with HKDF from the agreed-on master secret. In case a pre-shared key-only key exchange method was used, the server finish message containing a key derivation from the pre-shared key actually also authenticates the server, as with pre-shared key-only key exchanges, no server certificate is sent. If all the finish messages received are as expected, then the client and the server have authenticated each other where needed and have mutual assurance that their respective peer calculated the same master secret. With this, it's now clear that if this TLS 1.3 handshake was successfully executed, a secure channel has been constructed between the client and the server, even if the client and the server have never met before. I think this is absolutely amazing, don't you think?